Okay, and we're recording. So, new topic for today. We're talking about change of variables. As usual, I'm going to, sometimes in this course I'll use my Math219 notes because I think they're a little cleaner. So this is one of those times. It's all the same stuff, though. Although there will be a few moments in today's lecture where I'm going to gloss over a few points that, as they're written here, are use prerequisites that we don't have in this course and don't matter anyway, right? So I'll point those out as we go along. Okay, so change of variables is our topic, so I'm going to start by talking about the substitution rule that y'all will recall from single variable calculus. And I know y'all know the substitution rule. Here it is. Right? Y'all have written that down a million times. Y'all know how to do it, etc. What I'm going to do is give you a different point of view on it that I think is really helpful. In particular, this is going to be the model, the one-dimensional model on which we base what is in fact a generalization of this to higher dimensions that is change of variables, right? So so we need to take the right point of view here so that we can move along. Okay, so we've got this function called g, right? G is the thing that we're setting equal to x. That's our substitution. And notice that function g can be thought of as, well, literally a function with a domain over here and a target over here. You don't normally think of it that way in a Calc 1 class, or 1 or 2, or wherever this gets covered. All right, let's see here. So now these bounds, a and b, and this integral over here correspond to g of a and g of b. What's happening there? Well, I claim what's happening is that this domain for the integral on the left, if you look at individual points, like where does a go by this function? Where does a go? Well, the output value is g of a. And where does b go when you plug it into this g function? Well, the output value is g of b. Right? So really all this is saying is that the domain for the integral on the right is the image of the interval on the left. So that's, anyway, like I say, perhaps a different point of view from what you've seen before, but there's that. A couple other things. I'd like to introduce the idea that there's something called a pullback happening here. The idea of a pullback is a little bit weird of an idea. In fact, let me start off by coming up here, some blank space, and just kind of writing something down. This is going to seem a little silly. But if I were to have a function, I'll go ahead and call it g, why not? Where t is the input and x is the output. And let's suppose that this function g of t is t squared. Let's just say, right? Well, this function goes left to right. Inputs are on the left, outputs are on the right. But when I use this formula here for plugging in purposes, expressions that I plug into go right to left. I know that seems weird, but they go backwards. Commonly, we say they pull backwards through the function g. Let me give you an example of what I'm talking about here. If I have a function over here on the right, such as, let's say, sine of x, right? This is in terms of x, so I'm thinking of this as an expression on the right. If I plug in, let's see here, if I plug this into there, right, well, the result is sine of t squared. And notice that this act of plugging in has literally taken the expression that was in terms of the right variable and it has rewritten it in terms of the left variable. This is a little counterintuitive, right? But plugging in effectively pulls expressions backwards through the functions. That's all I mean by a pullback. It's not really all that big of a deal. There it is, right? I mean, clearly this works. Okay, so I'm going to view what we've got here as actually being a pullback. This expression here is what you get when you plug in for all the x's that are over here. That's just a way of thinking about it. Now, again, you can see the pulling back happening, right? We've got this function g that says that x is g of t, right? And playing around with differentials, you can persuade yourself that here's the differential of the output variable x, right? So x is g prime dt, or you might say differently, g prime is dx dt. Right? Just kind of moving things around a little bit. So this dx here is g prime dt, and I think y'all have seen that little move pulled, no pun intended, many times back in single variable calculus. Okay. All right. So that's one of the big points of view that I want to take on the substitution rule is it is a pullback. Right? And in particular, notice that as part of the pullback, it is an integral on a domain that is the image of the pullback domain that this integral pullback happens. Okay. All right. Okay, last point of view I want to take is I want to sort of reconceive of what's going on with this equation here. What is that? How do I think about that? And again, we have previously thought of this as being algebraic games that just the notation that we use for derivative and et cetera, purely algebraic point of view. But I want to point out this little thing here called dt. I can think of as being a size of a subinterval over here on the t-axis, right? And this little thing dx here, I can think of that as being, well, the size of the image of that thing over here on the x-axis. So I can literally think of what g is doing to this little interval, that it is taking that interval of size dt, whoops, I kind of missed, and producing a little subinterval of size dx. And now what's the purpose of thinking of it in that way? Well, the purpose is that I can then sort of reconceive of what g prime is doing. Don't think here of g prime as being a slope. Don't think of it as being a speed. Think of it as this is what you multiply the input size on the left. This is what you multiply it by to get the output size on the right. So this g prime is, we're taking that small blue interval and we're stretching it out to make it, it turns into this larger green interval here, and g prime is the factor by which its size got stretched. So we call that a stretching factor. So, different point of view. Again, you probably haven't thought of it this way before. That's okay. But this is the take on the substitution rule that's going to allow us to generalize. Okay, is everybody kind of willing to play along with these points of view? Is that all cool? All right. Okay, so what I'd like to do now is do the same thing in 2 dimensions. Totally analogous thing. Here we go. Let's suppose I have a nice domain over here. I've drawn it as a rectangle. It doesn't have to be, but the idea here is I want to think of the left domain as being the nice one. This is the one that we like. Right? Now, if I take this domain that we like and if I put it into this function g, golly, that's not a linear function. It could distort our domain substantially. This could be unfortunate, right? It could end up being kind of a wonky shape like that, or worse, conceivably, right? So we think of that as being a bad thing. So what I'd like to do now is consider this integral over here on the right side, over on the output side, this particular integral, and let's ask if we can do a pullback. Right, so the idea of a pullback, again, is that if you have an integral on an image in the target of a function g, right, an integral on that image, we should be able to rewrite that as an integral happening over here in the domain, right? That's what happened over here. An integral on the image in the target got pulled back to an integral on the pre-image in the domain. Right, so analogous thing. So supposing we have this setup, I've got this green set, I've got this blue set, I'd like to just pull it on back. And the good news is everything just works out just fine. There's nothing stopping us from doing this. In particular, keep in mind when we write down that g is the function, what this means is that x and y are the images of u and v. And that means that x comma y is g of u comma v. So this is one of the important elements of the pullback, is that you're literally just plugging in where you see the output variables. You plug in those formulas to write them in terms of the input variables. That's all that is. And then there's this idea of a stretching factor, and now I'm going to clear off all of what's going on here. On the coloring is just kind of making a mess, and I want to have a clearer space. But I've got to entertain the question now of this little piece of area over here, being as it is the image of a nice, pretty little square over here, a rectangle over here. How much does this get stretched out by the action of that function? What is this area? I wanted to be in the highlighter mode. What is this area here, dA? Right? And how would I rewrite that in terms of this little area over here, which of course is just du dv? And, well, again, it's going to be bigger it's not going to be the same, right? Everything got stretched out by the function g. So it's going to have a different size. I've drawn it here as if it's bigger. Of course, it doesn't have to be. It could be smaller. But there's a factor by which the area on the left has gotten multiplied. And what that factor is, as of this particular moment, I'm just going to call it the stretching factor. There is some factor that you multiply by the green area to get the blue area. Is that cool? Okay. All right. So we'll talk about what that stretching factor is in just a moment, but the point is, notice what's happened here in total. We had an expression, an integral, defined on this domain on the right, which again, I claim we don't like. We'll talk more about that in just a moment. But this integral on a domain that we don't like has now been transformed, right, equal in value to an integral that we've got defined over here on our original domain. You might call it the pullback domain, I like to call it. On the left, which is presumably nicer. And so that's the big payoff. This is why we care about this kind of what you might call a two-dimensional version of the substitution rule. This two-dimensional pullback is it turns an integral over a bad domain that we don't like. I mean, oh my, but let's belabor for just a moment. Why do I not like this domain? Oh, because when I start slicing it up, I'm going to be hitting corners, right? I'm going to hit a corner there as I slice vertically, and then I'm going to hit a corner here as I slice vertically, and then, oh, you know what? I think I'm going to hit a corner there. Before I quite get to the end, I'm going to have 4 separate integrals there. Yikes. Right? This is, oh my gosh, that's going to be super inconvenient. We do not like that blue integral on the right. But if I can pound out the little details, and again, there is this big looming question of what that stretching factor is. If I can figure out what that stretching factor is, effectively this means I can just throw away that blue integral. I don't need it. And instead, I can compute this integral over here on everybody's favorite domain for a double integral, namely a rectangle. Much nicer. Constant bounds. No corners. Really nice. Is everybody on board? Okay. All right, so that's the big idea, and now the looming question: what is this stretching factor? There is a perfectly reasonable point of view on how to compute this stretching factor and how to justify the formula for this stretching factor, and tough choices and all that. We just don't have time to cover that in this course. So you're not going to be responsible in this offering of Math 212. You're not responsible for knowing why the formula I'm about to show you is what it is. I'm going to make a vague reference later in the notes to a calculation you can follow through on your own if you're curious. But you don't have to. You're not responsible for it. I'm just going to tell you what that stretching factor is. And here it is. The stretching factor formula is this right here. It's the absolute value of the determinant of the derivative matrix, sometimes called the Jacobian matrix. Y'all will recall this from our conversation about differentiation and directional derivatives and chain rule, right? This is a matrix has made several appearances in the past. But just as a reminder, this stretching factor here, this formula, is a reference, again, to this derivative matrix that is, in fact, just this right here. It's the partials of the output variables with respect to the input variables arranged in a particular way, nicely organized, natural kind of a way. Right? So here you have an explicit formula for how to compute your stretching factor. Is that cool? Is everybody willing to buy it? Okay. All right. Now, real quick before I go on, this determinant, and no absolute values included. Notice the determinant itself inside of the absolute values. There is an alternative notation for that determinant. That alternative notation is this right here. I have a hair on my screen there. So this little weird little notation, and it's kind of strange looking at a glance, but let me give you two motivations for why we like this notation. For one thing, it literally says in how it's written, it's as if it's saying we're taking the derivatives of all of the output variables with respect to the input variables, right? So, I mean, it is kind of believable, right? That's kind of nice. You can see right here the output variables, X and Y, and you're taking the partials with respect to the input variables, U and V. Yeah. Here's another reason, and I think arguably a better reason. Whatever. Here's if I were to use this notation here for my stretching factor, and if I were to let me just write it down. Here we go. Absolute value, partial XY, partial UV. There's our stretching factor. And that's what I am multiplying, recall, times, let's see, you know what, I really like to use green for this, as we have in the past. Multiplying by du dv. There. Right, so I've got stretching factor times du dv. And that's supposed to equal to, let's see here, blue, area in the xy plane, which plausibly could be denoted as dx dy. It's as if we're saying that is equal to this, which really kind of makes, I mean, look, now I'm about to commit a math crime. Right? Don't hold me to it. Please don't tell my high school, my college calculus teachers that I'm about to do this. Right? They'd be aghast. Right? Because this is not true, but it looks like the du dv cancels, kinda, doesn't it? So now that's a math crime that didn't happen. After all, I could not emphasize enough. This thing right here It's not a fraction, right? I know I've written it as if it's a fraction, but that doesn't mean it is. What it very clearly is a determinant. A determinant is not a fraction. So there is no cancellation. What I've just done there in red is garbage. But it sure is convenient and intuitively satisfying garbage. And let me say it a little bit differently. If things line up in such a way that these appear to cancel, garbage though it is, then you have it set up correctly. And it's really easy to accidentally get your stretching factor put in backwards or on the wrong side. We're going to see some examples of that in a few minutes. But it's very handy to have it, this faux cancellation always lines things up correctly. So, again, there are certain kinds of notations that are actually kind of nonsense that I really like, right? And this is one of them. Okay. How we doing? Example coming up. So yeah, here we go. We have an integral where the domain for the integral in the xy plane is this shape right here. That's my domain for this integral. And that domain is defined as being the image of the unit square over here in the UV plane. So this is our setup, right? Notice the way the problem is written. Just read it straight out. That's what describes the picture I've got going here. I'm given that my domain for the integral on the right is the image of the unit square on the left. Right? Free information. By the way, I do realize that makes this problem seem highly manufactured and implausibly, unrealistically convenient, and that's true. I just want to get a win in the win column, right? First, let's see how this change of variables formula works in practice. Let's get a win on the scoreboard, and then we'll talk later about more plausible, more realistic scenarios and how to come up with your own change of variables function and how to figure out what your pullback domain is, things like that. Okay, so anyway, for the moment, manufactured, setup, kind of an example. Is everybody with me so far? All right, so and our goal is going to be to compute this integral here on the right. How are we going to compute it? Well, I'm going to pull it back. I'm going to rewrite it in terms of an integral on the left. And in order to do that, I'm just going to use this formula right here, the one which I've left a mess. Let me clean up my mess. I'm just going to use this formula where the formula says, yeah, you want to take an integral on the right and rewrite it as an integral on the left? Okay, cool. Don't forget to plug in for what your output variables are. That's just plugging in. No tricky curves there. That's just literally write down the formula for what x is in terms of u and v. Write down the formula for what y is in terms of u and v. That's just plugging in. Right? And then don't forget your stretching factor, right? Don't forget that the little piece of area on the left is not the same as the little piece of area on the right, and that you have to, as part of the pullback, you have to recognize by what factor is area on the left multiplied to get area on the right. In other words, don't forget to stick in there your stretching factor. Right? So this is the beautiful thing about change of variables, is it kind of all boils down to, you want to pull back? Okay, cool. Just don't forget your stretching factor. It's the one thing, it's the one part of this process that isn't just sort of like, well, of course. Okay, so anyway, here we go. So we're going to need to know the stretching factor. Right now we've got this formula right here for our function. Notice the input variables u and v, the output variables x and y. Notice that means that I have an explicit formula for what x is. X is this first output coordinate of our change of variables function. And y is the second coordinate of our change of variables function. And with that said, I'm going to compute our stretching factor. Correction, I'm going to compute this little, this is called the Jacobian determinant, by the way. After all, it is the determinant of the Jacobian. That's the name, Jacobian determinant. So I'm going to compute that first. I do have to recognize that our stretching factor is actually the absolute value of that. We'll get to that in a minute. For the moment, let's just compute the Jacobian determinant. There you go, determinant of the derivative matrix. Now, real quick, how did I get this derivative matrix? Don't forget what the derivative matrix is. It's the derivatives of the outputs with respect to the inputs. And you got to do those, all four of them, four little partial derivatives. In particular, notice that that column is just the partials with respect to u, right? And this is the partials with respect to v. That's just, the old familiar formula from last week or whenever that was. Okay. Make sure you can do that. Make sure you can compute, not only compute the partials, but that you're crisply clear on how to assemble them to make that derivative matrix in that particular order. Okay, and computation of determinant, no big deal, and you get this for our Jacobian determinant, and it's tempting to just walk with this. Problem though, keep in mind, that thing, we do have to take its absolute value. The absolute value is critical. This is not a minor formality. It's got to be the absolute value. And again, reasons are, there's a long conversation there that we're not gonna worry about. So how then do I take the absolute value of 4uv minus 9? And in this case, it works out really nicely, very conveniently. It's tempting to kind of be like, I don't know, I guess some values of u and v, maybe this is positive. For other values, it could be negative. How do I decide? The convenient little observation to make here is that I can see u, the variable u, not you personally. I can see u in this picture. Here it is. I've got a new domain. It's that unit square. That was given as the pullback domain, and I can see right there in the picture that u is always between 0 and 1. And likewise, I can see right here in the picture that this v right here is always between 0 and 1, as it turns out, on our pullback domain. And so this expression, this thing that I'm interested in, the absolute value of, that thing, well, let's see here. U and v are always less than 1. That means 4uv is always less than 4. If I subtract 9, that's always less than or equal to negative 5. This thing is always negative. Is that cool? Everybody on board? So I am taking the absolute value here of something that is always negative. And the way you take the absolute value of something that's negative is you compute the negative of it. Right? Is everybody comfortable with that? By the way, the algebra of absolute values is an underappreciated topic, I think. It's an underemphasized topic in most high schools. That's just my opinion. But they come up significantly in the real world, and at least in my high school, there were definitely a lot of teachers who would studiously avoid absolute values ever coming up because it's weird and they don't want to mess with it, and they get confused themselves. I would be surprised. And so a lot of students get to, college math class without ever having to really deal with absolute values very much. So make sure you're comfortable with that stuff. And I do have a discussion of some interesting facts about the underappreciated algebra. I've forgotten what I call it, but I think I called it algebraic pitfalls. It's in the miscellaneous topics playlist on my YouTube channel if you want to give that a look. Okay. So anyway, there's our stretching factor. Absolute value and all. Our stretching factor is this, and now it's all over but the shouting. I have these little pieces of area on the right. and I know how to pull them back to write them in terms of area on the left. All I have to do is insert my stretching factor, which I've done there, and everything else is just a matter of plugging in. All right, so again, don't forget, easy to lose track, but X is that thing, so plug it in. Right? Y is that thing, so plug it in. The plugging in part is kind of just a matter of doing it. You do have to remember what you're plugging in and where you find what you're plugging in. Right? And just keep in mind, what you're plugging in comes straight out of the change of variables formula itself. But the act of plugging it in is no big deal. So again, the only non-trivial piece of this is computing and inserting this stretching factor here. And having done that, we're good. Our integral that we started off with, let me just remind you, we started off being interested in this integral right here, defined on that pullback domain, which we don't like because it's all distorted and weird and corners, and there's all sorts of reasons I don't like that domain, right? But we have now successfully rewritten that as an integral over here on the left. The pullback domain, that's not happy enough for my tastes. There we go. So much nicer integral because the domain is much nicer. Yeah?
Is the reason why the left one's much nicer is because on the right one, it's the basis vectors are x and y?
The reason... yeah, we don't have to bring the unit vectors into it. This is really much simpler. Is that if I were to try to compute an integral on this domain, I'm going to hit that corner and that corner, right, in my slicing process, and it doesn't even matter which way I slice. I could slice the other way, and I'm still going to hit both of those corners. And so this is actually 3 separate iterated integrals. That's really that's the first ugly thing about it. The other ugly thing about it, and I hadn't really gotten to this, is notice that as you're doing any one of those integrals, for example, you're going to need to know the equation of this curve. The equation of a curve is a relationship between x and y. So I would have to figure out some algebraic relationship between these two expressions, and oh my gosh. Right, that would not clear exactly how you do that. Right? So there are a lot of things that I don't like about that domain on the right.
Okay, and then
yeah. Oh yeah. Go ahead.
And then for the point area on the right side, we'll move it back to, since the point area, say point mass or something, on the right side will be like a parallelogram, and then you move it back to like a rectangle, or like square.
Yes.
Okay.
Yeah, you're touching on an issue that I also swept under the rug. You may recall when I defined integrals, I define integrals by always slicing up regions into little bitty rectangles. Turns out you don't have to do that. There's nothing particularly wrong. If I were to take this square, for example, and just a quick digression, if I were to take this square, and if I were to slice it like this, right, the whole is still the sum of the parts. There's really nothing wrong with such a slicing. And it's weirder and it's harder to work with, and why would anyone ever want to do something so unnatural? Yeah, fair. But I could. There's really nothing wrong with that, right? So the fact that these are rectangles and these are not rectangles is actually not really such a problem. That's just a shortcoming, you might say, in how we've defined integrals, but it's a formality and it's not something you need to worry about. The problem is that just very simply, as a domain, this is a hard domain to work with, and I don't like it.
Okay, yeah, because that's just my intuition for where the stretching factor came from.
Yeah. Oh, yeah. No, that's right. Absolutely. Yeah, that's very largely the point. Yeah, there's a couple of little details, but yes, absolutely. Yep. Okay, now you had a question.
Yeah.
Okay.
Yeah, is the right one S and the left one D? What were the S's?
Let's see here. Yeah, so let's see here. So the one on the left here was called S, and that's our new domain. And the one that's on the right here is what we had originally called D, which was our the one that we didn't like. Yeah. Okay, so in practice, this is actually a pretty easy formula to work with. Just don't forget your stretching factor, and otherwise, yeah, cool, go ahead, plug in, pull back, use the pre-image domain is fine, right? Okay, now, again, reminder, this previous example we just saw, highly manufactured, I just gave you for free what the change of variables function was, and that makes it unnatural and a little bit of a freebie. So how would you dream up your own change of variables functions? Just do keep in mind we are pulling back, we're not pushing forward, and so there's sort of an oppositeness. But in particular, if you use this as a change of variables function where all of the points you add a comma b to all the points as you go from left to right. When you pull back, that's going to kind of undo what the g function does. And so the result in the pullback is that if this is your change of variables function, then your domain's going to get kind of translated backwards, or translated by minus a comma minus b. Right, so this is backwardness of it. And so likewise, a magnification done backwards will squish your domain. If your change of variables function is a counterclockwise rotation, when you pull back, it will effectively clockwise rotate, etc. So just keep that in mind. I'm going to show you an example now of this one. We're going to use a rotation as a change of variables function. This is the first instance where I'm going to have to kind of wave my hands at some linear algebra, right, that y'all are not responsible for knowing because Math219, linear algebra is not a prerequisite for this course. Anyway, so we'll get to that in a second. We're going to start off with needing to compute an integral on a domain that's a square with corners at certain locations that are given in the xy plane. Those are those four locations, and here then is the resulting square. I want to do an integral on this square. Right? I mean, come on. I'm going to slice through that corner and that corner. Or if I slice the other way, then I'll slice through the other two corners. But if I were to just go directly brute force at this as a domain, I'm going to have to break this up into three separate pieces. Right? So we don't want to do that. Bummer. Okay, you know what? Let me just go ahead. Okay, so what I'm going to observe is that this square that I've got, highlighter, this square that I have is a counterclockwise rotation. Of what you might think of as being this square that I'm drawing in green there, but just to avoid confusion of variables, of course, the pullback domain needs to be in terms of I'm using u and v. You can use s and t if you like; it doesn't matter. But I'm going to draw it over here on the on the left to emphasize that this function that I'm going to call t. This function does a counterclockwise rotation, and that counterclockwise rotation turns the green square into the blue square. Is that cool? All right. Now here's where I'm going to invoke some linear algebra. You're not responsible for the following. How to do a counterclockwise rotation around the origin by an angle theta. If you've had a linear algebra course, you can make sense out of this, and it's a nice little exercise. If you have not had a linear algebra course, no problem. No problem. Just here's the answer. It turns out that multiplication by this matrix. That's what does it. And in particular, the angle theta here is the angle by which you're doing the counterclockwise rotation. And you can look at the numbers that we were given here, right? Keep in mind, we know these points. So, for example, that point right there is that point right there. And a little bit of trig in the plane will persuade you that that angle is pi over 6. That's good exercise. Make sure you're good with your trig. I've said that enough times. So anyway, make sure you're comfortable with that. Okay, so again, what I have in orange here is free information. You are not responsible for understanding why, but I just do want you to know that this matrix does what I'm claiming it does, a counterclockwise rotation. Okay. Is everybody willing to accept that? Okay. All right. So, we can plug in this value of theta. We can compute this matrix. It's that right there. Which, by the way, gives me an explicit formula for x. For example, x is that dot product. And y is that dot product. Right? So now I have an explicit formula for x and y in terms of u and v, and computing off we go. You can compute your Jacobian determinant. Easy computation, a couple of partials, easy partials no less. Assemble them as a matrix, take that determinant, and it turns out the answer is 1. So, details. Good exercise to follow through. Make sure you can plug that all in. Now, I am going to point out that this is what I like to call geometrically expected, because after all I did was rotate, right? This square, and it's what you get when you rotate it. If you just rotate, that doesn't make anything bigger or smaller. So, of course, all the areas are the same. Of course, therefore, my stretching factor is 1. Now, geometrically, does everybody buy that? Okay. Now, that said, just because it is geometrically evident, right, doesn't change the fact that, again, this is not a course about answers. This is a course about reasoning, and I don't want to prove this fact. And more to the point, what I'm interested in and what is, the relevant skill for this course is being able to do this calculation. Right? So please do make sure that even if it's geometrically obvious what the stretching factor is, please do show the calculation that is going to be assumed and required for this course. I hope that's all clear. Okay. All right. So it's all over with the shouting. We have this expression here, 2x minus y. Oh, don't forget, though, x, we already know, is that dot product. So this x right here is that right there. And we've also got that y. Okay, well, yeah, but don't forget y is that dot product. So plugging in, right? All I'm doing is plugging in. No tricky curves there, right? Don't forget your stretching factor, though. We already just computed our stretching factor. Now, another sort of point of order. Even though the factor is 1, even though that factor, therefore, doesn't really do anything, I think it's really good form to go ahead and stick it in just so it's clear that you knew what to do with it, right? Now, again, keep in mind, your goal as you write is not just to help you keep track of stuff that you can't do in your head. Your goal as you write is to communicate to the grader what you understand. And so, unnecessary though one could argue this is, it does help the grader see, this student not only computed the Jacobian determinant, but knows where it goes. Does that make sense to everybody? All right. And so, big win, because our original integral, keep in mind, our original integral was on this domain right here, which we don't like because it's cornery and stuff. That integral we have now rewritten as a new integral on a very cleanly oriented square, no less, in the UV plane, and this green integral is a much easier integral to compute. Now, I know what you might be thinking. You may be thinking, this domain was a lot nicer, and this integrand. This integrand was a lot nicer, and this integrand is looking weirder. True. But you only have to do one of these. And in fact, the weirdness is just constants. So it's not even really all that much weirder. It's just constants, right? Whereas this over here, you got to do 3 separate integrals where the bounds are not constants, where the bounds, you'd have to do some geometry work to even figure out what the equations of those lines are and stuff. What we have on the left is much harder. Doable, much harder. Is that cool? Everybody happy? Okay. All right. Okay. So here is a twist. I got ahead of myself. A couple of quick comments. And again, I don't want to get bogged down in all of this in Math 212. But as a point of order, in order for the change of variables function to be something that you can use in the way that I have been, it is necessary that the function be continuously differentiable. We're not going to get bogged down in that because all the functions we're going to choose are going to be continuously differentiable. So nothing to worry about there. Also, they all must be invertible. And this is another, it can be a sticky wicket. But there's 2 possibilities for a change of variables function. One is that it's perfectly obvious that it's invertible. Like a rotation, right? If you rotate, you can rotate back. It's very clear. There's nothing to talk about there, right? So that's possibility number 1, that it's perfectly obvious the function's invertible. Possibility number 2 is that it's really hard to show that the function is invertible. So this is another thing that I don't want to get bogged down in this course. Any change of variables scenarios that I give you, the clear and obvious choice based on techniques that I'm going to show you for what change of variables function to use, I'm going to arrange it to where these will not be issues. Okay, so now, let me point out, there's no law that says that functions have to go left to right. Right? So for example, now what we've been looking at is a function that goes left to right where x and y are functions of u and v, and there's our stretching factor. Notice in particular that the stretching factor is the partials of the output variables with respect to the input variables. All right? Okay. Well, I could invert that function. If I have x and y as functions of u and v, I might be able to do some algebra. Certainly in the abstract, being an invertible function, I should be able to solve for u and v. If you solve for u and v, then u and v are the output values now. X and y are the input values. And so same formula for your stretching factor. Partials of the output variables. U and v are now the output variables. With respect to the input variables, x and y are now the input variables. Right? And so that noted, check it out. Doesn't it look like these stretching factors, they look to be inverses of each other, don't they? Because they're fractions, and when you flip a fraction, that's the same as a reciprocal. Oh wait, whoops, no, these are not fractions. That's just notation that we made up because we're, I'm going to say lazy kind of, but it's very convenient though, right? So we've made up this notation just for convenience. But you got to remember, they aren't fractions. And yet, here's the good news. They actually do behave like fractions. Because after all, let's think about this process where I have some little piece of area over here. And, oh man, my elbow. some little piece of area there. And what would happen if I did this, where I take that area, I push it over to the right, and then I pull it back to the left? Well, altogether, nothing happened. Altogether, I get the exact same area that I started with. Overall, that stretching factor is clearly 1. But also, what has happened is I've done a, let's see here, color choices. I've done a stretching factor, whoops. There is the first stretching factor that keeps track of what happened in sort of the first half of that process. And then there is the second stretching factor that keeps track of what happened in the second half of that process. Right? So altogether then, this product is equal to 1, which means that indeed these things are reciprocals of each other, or said differently, even though they're not fractions, they behave like fractions, which is another nice little motivation for why we write them as fractions. It's because they behave like it. The second way in which these behave like fractions. Is that cool? So, nice little convenience. Let me show you how this can be really, really useful. This example here, now there's a bunch of work that needs to be done to develop this example. It's going to be a few minutes before we get to all that fractions business. This is going to look like a weirdo manufactured example. It's not. This comes up very naturally. I took a thermodynamics class in college, part of the physics major, and it turns out that if you're interested in doing computations related to what's called the Carnot engine, which is a theoretical construction that helps you understand how thermodynamics works and engine efficiency and stuff like this. Turns out that you end up having to do integrals on domains that look like this. I didn't do it, right? This comes up naturally. And in particular, these two curves have equations like that, and these two curves that make up the other two edges have equations like this. And not exactly, I did streamline this a little bit. It turns out that the exponents there are not integers. It's a little weirder. It's a little bit weirder than this. But close enough, right? Structurally, it's the same as this. Okay. So, again, doing an integral on a domain like this is extremely natural physically. And if you, as engineers, probably, if I wild guess, I would guess mechanical engineers would have to take a course in thermodynamics, and maybe other engineers. It could be, I don't know. But anyway, it's entirely possible you may need to, you may see exactly, or close enough to exactly this domain come up in your engineering futures. Okay. All right. So that said, how would I deal with this integral? Notice we don't like this domain. It's got corners all over the place that are weird. This is going to be 3 separate integrals. Nobody likes that. So what I'm going to do, and I wish I thought of this myself, but I didn't. I'm going to show you just like someone showed me. The clever idea is as follows. The xy, call those u. The xy squared, call that v. I didn't think of this again. Somebody showed me. If you view that as a change of variables function, like so, going backwards, notice. Right? So we're going to have to worry about the which way is on what side. Do we stretch or we squish? Are we undoing a stretch? We'll get to that in a minute. But notice something really nice happens here. And so, for example, if I were to look at these two curves, xy equals 1, xy equals 2, these weird curves over here, close enough, those curves in the xy plane, well, if u is xy, and if xy is 1, then that just says u equals 1. Just straight vertical line in the UV plane. Likewise, if u equals xy and if xy equals 2, okay, well then u equals 2, another straight line in the xy plane. And likewise, these two equations here, these two curves also become straight lines, these horizontal. So, pretty cool. Our weirdo domain turns into a rectangle. Everybody on board? It's a neat trick. I wish I thought of it. You don't need to have thought of it. You need to remember it. So, okay, now let me say a couple of more quick words about exactly what makes this trick work. Do notice that in order to have this, like I was saying before, that, u is xy and xy is 1, therefore I get u equals 1. In order for that to work out as a nice straight line, I do need that to be a constant. U needs to be a constant, which means that this formula over here needs to be stuff equals constants. Said differently, we need to have these equations written as level sets. Stuff equals constants. That's critical to make this work as nicely as it did. So if the equation comes to you not written in that convenient of a form, so for example, let's suppose hypothetically that you'd gotten, x equals y plus 3, something like this. Don't work with x equals y plus 3. Rewrite that as x minus y equals 3. That's the one you want to work with, because you need that constant on the right to make it the result turn into lines, which means that it's x minus y that needs to be your formula. Not x, not y plus 3. Is everybody good with that? All right. Okay. All right. So now we're going to need to know the stretching factor. I can take my outputs. Keep in mind now that u and v are my outputs, because there's my formula. U and v are the outputs. And I can take their partials with respect to the inputs. Clearly x and y are my inputs. And I can just take those partials, no big deal. My Jacobian determinant ends up being that. Seems easy, right? But here's the problem. What I need here, and here's the process of me taking our original integral that we're going to try to compute and turning it into something that I claim is easier. Notice, I'm going to need to know what to multiply by du dv to get dx dy. Said differently, I need to rewrite dx dy in terms of du dv. Said differently, I need to know what it is that I multiply by du dv to get dx dy, and the faux cancellation that makes that work. Here it is. It's got to be partial xy, partial uv. That's what I need. What I have computed, unfortunately, is not. Oh, I used a bad color choice there. Sorry. This is what I want. But this is what I have. Does everybody see what happened there? This is unavoidably. I had to compute partial UV, partial XY, because that's what I have formulas for. That's my only option, but I need the other one. This is where it's very convenient to know that these are reciprocals of each other. So fine, if you compute the wrong one, no problem. Just flip it. Right? Take the reciprocal. And so that's what I'm doing here. Notice if partial UV, partial XY is that, then partial XY, partial UV is the reciprocal of that. Yep.
Can you go over again how we know that we want the reciprocal of the inverse?
Yeah. So that's right. So this was the integral I was initially asked to compute. Is that cool?
Yeah.
Right. Okay, so this is what I want to compute. my hope is to rewrite that as blah, 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 blah times du dv, because the whole idea here is I want to rewrite in the UV plane. And the reason I want to rewrite in the UV plane is because, well, look at it. I'd like to rewrite in terms of this much nicer domain here, right? So, just kind of piecing the Legos together, this is what I have. I want it to be something like this. And so, what is this thing? I have to ask the question, what is the thing that multiplies by du dv to be dx dy? So, that's, yeah, right. Is everybody happy with that? Okay. So, yeah. All right. So, cool. We got it computed. Here it is. The stretching factor I need was not the one that I computed in the first place. It's the reciprocal of the one that I computed in the first place. Oh, let's give credit where credit's due. Gotta love this notation. This notation kept track of that for me. Right? So I really dig this notation here for that purpose. It does your bookkeeping for you. And as a result of that, with my stretching factor computed, that's that. My original integrand, of course, was that. And altogether then, my new integrand, stretching factor included, is this right here. Is everybody okay with that? And there's a problem. This comes up when you, roughly speaking, are doing your change of variables backwards, right? I'm hoping to pull back, but my function is not going backwards. My function's going the same way I'm wanting to pull. It's just not going the right way, right? And so this is going to happen when that's the case. And look at the problem. My integrand is written in terms of x's and y's. My differentials are u's and v's, which of course was the point, so that I could have nice constant bounds. But it remains that my integrand is in terms of the wrong variables. And it's tempting to say, okay, fine, just plug in for x and y. I don't have x and y. I have u and v. Right? So, annoying. What do we do? You have a couple of choices. You could try to solve for x and y. And in this case, it's not even hard. But in other cases, it is. So rather than solve for x and y, I think it's really important to note, we technically don't need to solve for x and y, because I don't have x specifically and y specifically that I need to rewrite. I really only need to rewrite x to the 7th times y. That's the only thing I actually need. I don't need to know x specifically. I don't need to know y specifically. So what I'm going to do then is just take this thing that I need, and I'm going to try to write it in terms of, well, u and v that I know how to write in terms of x and y. So I find myself with this scenario. Again, I've got, let's see here, I've got an expression in terms of x's and y's that I want to write in terms of u and v that are themselves expressions in terms of x's and y's. And here's where an algebraic game begins. Now, what I've got written down here is how I'm going to strategize on the basis of my current situation. And here's the strategery. The thing that I'm interested in is a product of powers of x and y. What I need to write it in terms of is a product of powers of x and y and a product of powers of x and y. Now, I have a rhetorical question. What would you do to products of powers of x and y to produce a different product of powers of x and y? And here's my proposal. I think that I should take a product of powers of the given products of powers to produce hopefully, fingers crossed, the relevant product of powers of interest. Doesn't that seem likely? I mean, if I have a product of I got these products of powers of x and y. I've got the green, I've got the orange, right? I get green and orange. I don't think I should expect to add them to produce the blue. I don't expect that I'll be taking the tangents or arc sine of green and orange to produce blue. It's just algebraically, it's just not what I would expect to work. Algebraically, if I had to guess, I would think products of powers is what you do to products of powers to produce products of powers, because that's how products of powers work. So now this is speculation. I write this with a question mark here, right? I don't know that this is going to work, but I'm highly suspicious that this is going to work. Now, does everybody see though why I'm doing what I've got in purple here? What I've got in purple is my speculation of what to do with my givens to produce what I need. Yes?
Why is the y in the second part squared?
Oh, that's just what the formula was for U and V.
Oh, okay.
Yeah, U and V are those things there. Yeah, right. All right. So, it's going to be a different guess every time, this form. That is how you form your equation that you're eventually going to try to solve to, put the pieces together to figure out what to do with your integrand. Always going to be a different sort of structure depending on what you're given. Here we had products of powers, so this seems like a reasonable guess. You might instead, for a different question, have linear combinations, maybe. I don't know, whatever. Right? So your guess is going to be different for every question. But let's proceed to finish off this one. In this case, I can take the right side and I can multiply that out. Now I can compare what I have with what I've turned that into, and notice that means that a plus b has to equal to 7, and it also means that a plus 2b has to equal to 1. And this is a little system of equations that I can just solve. What do they call it? Simultaneous equations. Technically, that's kind of a linear algebra thing, but this is a middle school version of it, so I think y'all can do that. And once you know the A and the B tells you then that this expression that we want is this product of powers of U and V, and therefore it's that. And that then is exactly what we plug in. Yeah, that was the red color. That is what we plug in for there, and it's all downhill at that point because U's and V's, integrals with U's and V's, and it's easy computation. Everybody happy? All right. This is the part that I'm going to skip. Again, if you're curious, you're welcome to give a look at this. What I've written here does use a little bit of linear algebra. So if you haven't had a linear algebra, you're going to probably get stuck partway through this calculation. But just to emphasize that you're not responsible for that, I'm going to put a big X through here. Okay, so you don't have to if you don't want to. But if you're curious, this is the big idea about where the stretching factor comes from. You can see the result right here. There's our stretching factor that comes out of this calculation. But again, not your problem. 3 dimensions. What if we're in 3 dimensions instead of 2? Right? Everything we've been doing here is in 2 dimensions. We were assuming that we had an area whose image was an uglier area, and that we wanted to pull back from the target area to the pullback area. All in 2 dimensions. So, well, what's the 3-dimensional version of this? If I have a volume, and I want to look at its image, and its image, oh my gosh, is going to be severe wonky. Just imagine the nightmare of having to slice up whatever that thing is. You're going to hit corners all over the place. And then worse, the slices that you'd be looking at, right? Let me just for fun here, just for the shock and horror of it all, the slices that you would be looking at here would themselves be messed up shapes that when you slice them up, you'd be hitting corners, right? So, oh my gosh, you'd be hitting dozens of integrals here. This is a nightmare if you go brute force on it. Nightmare. Okay. So very highly motivated then to try to do a pullback so that we can rewrite this as an integral over this green box, which of course, world's easiest domain for a triple integral is it's all lined up and flat and straight, and you never hit any corners. Doesn't matter which way you slice. It's awesome. Right? And so the pullback would be really nice to achieve, and just like when in 2 dimensions, yeah, go ahead. No problem. G explicitly tells you X, Y, and Z in terms of U and... Oh, come on, elbow. X, Y, and Z in terms of U and V. Plug it in. Nothing to it. Just make sure not to forget your stretching factor. By what factor are the output areas, volumes, bigger than the input volumes? Just don't forget to insert that stretching factor, and everything works out just fine. Again, there is a formula for this stretching factor. Again, you're not responsible for it. It's the absolute value of the Jacobian determinant, which again we have a nice notation for, totally analogous to the 2-dimensional version. It's the partials of the outputs with respect to the inputs, arranged as a matrix, of course. Determinant, of course. Cool? All right. Okay, so here is an example. Now, this first little theorem that I want to throw in here, just to get it out of the way, it's a neat fact. If you view matrix multiplication as a function, it turns out, assuming A is a constant matrix, it turns out that the derivative matrix is the same matrix. Now, y'all can just directly confirm this yourself. It's not that big a deal. Write down a 3x3 matrix, A, B, C, D, E, F, G, H, I, right? And multiply it out, write the formula, take the partials, assemble the partials. Oh my gosh, it's going to be the exact same matrix. Just a matter of direct computation. Okay. This example that I'm going to show you here is another example of where I am going to have to sort of streamline part of it. There is a little bit of linear algebra in here where I have students come up with their own change of variables function. I'm not going to make y'all do that in this case because it uses some linear algebra tricks that y'all are not responsible for. So I'm just going to handle that part directly. I'm going to make that a freebie as follows. Our target domain over here is a parallelepiped, and certain edge vectors are given to define that parallelepiped. And I'm going to give you as free information, even though it's written as something that's part of the analysis here, that the function that makes that an image is this function right here, where you multiply by this matrix being the one whose columns are these given vectors. There. Now, why that's true, don't worry about it. That's given for what we're doing here. Is that cool? So, change of variables function given. So this matrix, again, is the matrix whose columns are those given vectors. So with that formula given, all we have to do to compute this integral, and by the way, let's recognize what a nasty integral this is. An integral over this shape. As you start slicing, and it doesn't even matter which way you slice, the first few slices are going to be triangles in shape. And then at some point, they're going to turn into parallelograms. And then after a little while, they're going to turn into hexagons. And then they're going to turn into parallelograms again, probably. Anyway, it's going to get weird, right? Nightmare of an integral to do directly. But I can do the pullback. I already know, I have given in the version of the question I'm doing for you here, that by way of this function, the pullback domain is the unit cube, which is a much nicer domain. So pullback, and in doing the pullback, our domain, again, is awesome. And don't forget the stretching factor. The stretching factor, you do have to compute the absolute value of the Jacobian determinant. Make sure not to forget that. Then there's the question of, wait a minute, what do I do with the original integrand? My original integrand here, you'll notice, is z. That doesn't go away. How do I write z? What is z? Very importantly, z is one of the output variables. Let's look at this equation right there that says, and I'm going to come over here where I have some space. I've got a matrix times UVW that equals XYZ. And so I can tell you exactly what z is. Z, the third output variable, is just that dot product. So it's that right there, coefficients being that third row. And it's all over but the shouting. This integral is much easier to compute because it's an integral over a cube. It's a single iterated integral. Easy computation. Is everybody on board? Okay. Good place to draw the line. See y'all later. Have a good Thursday.